I want to show you some application of vector field, potential, exact differential, conservative vector field in physics, namely in thermodynamics. So as an example, consider 1 mole of ideal gas described by the state equation PV is RT. If we add some heat, then this heat will result in the increase of the internal energy plus some mechanical work that the system can do when it expands. If we have some gas in some vessel with a moving wall, then if the wall moves by some small amount dx, then the work done is the force times the displacement dx. But the force is the pressure times the area of this piston. But as dx is the volume, the increase, the change of the volume of the gas. So we have dq being du plus pdv. Now consider some special situations. First, if the volume is constant. Such a process is called isochoric process. Then, if V is constant, dV is 0, and the heat that we add to the system transforms to the internal energy alone. And this is proportional to the change of heat, to the change of temperature, and the constant of proportionality is denoted Cv as the specific heat with constant volume. Now consider the case when P is constant. Then the added heat is transformed into increase of the internal energy and the total work and the mechanical work done. And the change of the energy is CVT, and this is PdV. But if P is constant, then dV, or the change of the left-hand side in the state equation, is change of the right-hand side, RdT. And then PdV is RdT and if we again introduce the heat capacity with constant pressure, then we see that Cp is Cv plus R. Let's write it here because we will need it later. Cp, the heat capacity with constant pressure, is equal to Cv plus R. And now, in general, that means not necessarily constant volume, not necessarily constant pressure. If we take the differential of this, we have PdV plus VdP is RdT. And then we can write the heat, dQ, as the differential form with differentials dV and dP, namely du, which is CVdT, plus the work, which is PdV. But dt is PdV divided by R. sorry, dt is pdv plus vdp divided by r. Times cv plus pdv. And now we want to simplify this a little. So dv is multiplied by p and when we multiply by r and divide by r, not yet. So dv, okay, let's write it slowly. CVP divided by r plus p dv plus cv v divided by r dt. But if we manipulate this bracket a little, we can bring these two terms to common denominator, and we can factor out p, and we have cv plus r. But cv plus r is cp. So we see that dq is pcp divided by r dv plus vcv divided by r dp. And if we you remember f1 dx plus f2 dy, then the volume v now plays the role of x, and the pressure p plays the role of y. And f1 is a coefficient at dx, so this is the first component of our new vector field, and this is the second component of our new vector field. And we can ask the question whether this vector field is conservative, whether it has potential, whether this differential form is or is not an exact differential. And you may remember that the condition is that the first component with respect to the second variable should be equal to the derivative of the second component with respect to the first one. So let's take the first component and multiply with respect to the second variable, which is cp divided by r. And the derivative of the second component of the vector field, partial derivative with respect to v, is cv divided by r. But they are different because cp and cv differ by some positive constant. So this is not true. So this expression as a differential form is not an exact differential. And if you travel in the dt plane from some point to another point, then the heat that you must add to the system depends not only on the endpoint and initial point of the system, or the end state and initial state, but also on the details of the journey, of the path. It is not path independent. This can be illustrated by the following example. Consider the initial point with volume V1 and pressure P1, and the end point with volume V2 and pressure P2. And consider going this way and this way. What will be the total heat that we must add to the system? Let's call it case 1. If we go this way, then P is constant, so we just integrate this one. P Cp divided by R. And because P is constant, integrating the constant means the constant times the change of the independent variable. PCP divided by R times the change of the volume. Plus, and when we go along this way, along this path, then now V is constant, so dV is 0, and we just integrate this. But now V is constant, so this is constant, and we integrate the constant, so the integral is the constant times the change of the variable P. So we have VCV divided by R times the change of pressure P. On the other hand, if we go, let me change the color. If we go from the same initial point to the same final point, but this time over this yellow path, then in the case 2, Q, let's call it Q2, and let's call this Q1. Then first the volume is constant, so dV is 0, and we integrate VCV divided by R, and V is equal to V1, so V1 CV divided by R times delta P. Sorry. That was PDP, not PCP, not C. And it was here when the pressure was P1, sorry. And the volume here was V2. Right. Plus this horizontal line. Now P is constant, so dP is 0. And we integrate PCP over R, but now P is P2, so we have P2 Cp divided by R times the change of the independent variable, which is delta V. Well, this is different. This is not so easy to see, but if we consider the difference, Q added in the second way minus Q added in the first way, which would be equivalent to the Q necessary to put to the system if we go around the closed loop. So yellow minus white. We have delta P multiplied by CV divided by R, and V1 minus V2, which is minus delta V. Minus yellow minus white, and delta V is multiplied by P2 minus P1, which is delta P, Cp divided by R delta V. We can factor out delta V delta P, and what remains is CV minus CP. Sorry, this is plus, and what we have is CP minus CV, but CP minus CV is R, divided by R is 1, and this is the result, which is non-zero when the volume changes and the pressure changes. So you see, this integral is not path independent. It depends on the path, whether you use the white one or the green one, or the yellow one. But we can use one trick. If we take the vector field from this differential form, let's write it once again. dq being pcp divided by r dv plus vcv divided by r dp. And when we divide by the absolute temperature, capital T, that means from the state equation PV is RT, 1 over T means R divided by PV. So we multiply actually by this fraction, and we have dq divided by the absolute temperature, capital T. We multiply by R, so R goes away, and P divided by PV is CP divided by V dV, plus R goes away, and V divided by PV is 1 over P. So this is another differential form, and we can consider this the first component of some vector field, and this the second component of some vector field, and we can again check whether this vector field is conservative or not. But if you differentiate the first expression with respect to P, you get 0. And if you differentiate the second component with respect to the first variable, you get 0. You see? And this is true. So this differential form is already an exact differential. This vector field is conservative. It has potential. And the potential is called entropy. So we denote dq divided by ds ds. And S is called entropy. And this is a state variable. And we can find the form for S. If we integrate this, then Cp is a multiplicative constant. And when you integrate 1 over V dV, you get logarithm of V, possibly denoted divided by some constant V0. And if you integrate this, you have Cv, which is some constant, and integrating 1 over P is logarithm of P, denoted by some Pc. So we have illustrated that dq is not a total differential, it's not an exact differential, but if you divide by absolute temperature T, that means we introduce a new variable, new quantity called entropy, then this is already a state variable. The vector field is conservative, it has potential, and this is an exact differential. What is new here, besides other details, we started with this expression as the generalization of the formula for mechanical work. Originally, dx, dy were two displacements measured in the same physical units, say meters. And F1, F2 were two forces, again two components of the force, again in the same units. But now you see that the rho of x is now v, and instead of y we have p. But v and p have different meaning, different physical units. Pressure in pascals, volume in liters or cubic meters. So this is another interesting note, another interesting generalization.